Welcome to another deep dive, everybody. Today, we're exploring a link between math and something you might wear every day. Necklaces.
Yeah, that's right.
Necklace is math.
Yeah.
How do those two go together?
Well, we'll be looking at some excerpts from the online encyclopedia of integer sequences.
Of course.
Specifically, entry A00000031.
Okay.
And also the Wikipedia entry for irreducible polynomial.
So get this. We're going to see how something as simple as a necklace with two colors can unlock math concepts.
Yeah.
Like irreducible polynomials. Those are a mouthful.
They are.
Shift registers, things that move bits around in computers, and even musical scales.
Yeah.
I was skeptical at first.
Really?
But once I saw the connection, it blew my mind.
I bet.
Ready to dive in.
Absolutely. Let's start with the OEIS.
Okay.
Entry A000031 describes the number of unique necklaces you can create with a certain number of beads.
Okay.
Let's call that N and two colors.
All right.
But there's a catch.
Oh, there's a catch?
You can't flip the necklace over.
Okay, I think I get that. So, like, if I had 3 beads, and they could be black or white, how many different necklaces could I make?
You could make 4 unique necklaces, one with all black beads, one with all white beads, one with 1 black and 2 white beads, and one with 1 white and 2 black beads.
Okay, and I can see how those are all different even if I can't flip them over.
Exactly.
Okay.
And if you increase the number of beads to 4, you get 6 unique necklaces.
Interesting.
It's fascinating how the number of possibilities grows as you add more beads.
It is. And you mentioned that this idea connects to musical scales.
Right.
Which seems wild to me. How does that work?
Well, think of the beads as notes in a scale.
Okay.
And the colors as different tones. This OEIS sequence can actually describe the number of unique scales you can create within an N-note equal-tempered tuning system.
Wow, so the math behind arranging beads on a necklace can also describe musical scales. That's a connection I never would have seen coming.
It highlights the interconnectedness of different fields of study through the lens of mathematics.
So we've got necklaces and music.
Yeah.
But then things take an even more unexpected turn when you bring in shift registers. I'll admit, when I first read about this, I was totally lost.
Okay.
What do necklaces have to do with digital circuits?
It seems strange at first, but there's a really interesting connection. A cycling shift register is essentially a loop where you store bits.
Okay.
Think of them as ones and zeros.
Right.
With each step, all the bits move one position along the loop, and the last bit circles back to the beginning.
Okay, so it's like a continuous loop of information.
Precisely imagine a carousel where each horse holds a bit, either a 1 or a 0.
Okay.
The carousel keeps spinning, and the horses shift positions.
Yeah.
But the pattern of ones and zeros keeps cycling through.
So how does this digital carousel relate to necklaces?
The patterns of ones and zeros that emerge from these cycling shift registers actually correspond to the patterns we see in our 2-color necklaces.
No way. So by analyzing these necklaces, we're also indirectly learning about how certain digital circuits function.
That's the amazing thing about mathematics. It allows us to connect seemingly unrelated concepts in surprising ways.
Yeah.
And it gets even deeper than that if you subtract 1 from the number of unique necklaces you can make with Warren beads. You get the number of 1s in something called the lexicographically least de Bruijn cycle. It's a bit of a mouthful.
Wow.
But for anyone interested in computer science, it's a fascinating detail that speaks to the intricate connections between these mathematical objects.
It's like peeling back the layers of an onion. The more we explore, the more intricate patterns we find.
Yeah.
So we've connected necklaces to music and digital circuits. What other surprises are in store for us?
Well, this is where we enter the world of abstract algebra, specifically a concept called irreducible polynomials.
Oh, that sounds intimidating, but I'm ready to be intimidated.
It's not as scary as it sounds. Imagine you have a polynomial, which is like a mathematical expression with variables and coefficients.
Right.
An irreducible polynomial is like a prime number. It can't be broken down into simpler polynomials using the allowed building blocks, which are the coefficients.
So it's like the most basic fundamental polynomial, kind of like how prime numbers are the building blocks for other numbers.
That's a great analogy. Just like you can factor a number into its prime factors, you can often break down polynomials into a product of irreducible polynomials.
And I'm guessing this ties back to our necklaces somehow.
You guessed it, the OEIS entry A00000031 also counts the number of binary irreducible polynomials whose degree divides. And who would have thought that counting necklaces could also tell us something about these abstract mathematical objects?
This is blowing my mind. What's fascinating to me is how this seemingly simple question about necklaces has taken us on a tour through music digital circuits and now abstract algebra. Where do we go from here?
Well, let's explore how this idea of irreducible polynomials helps mathematicians study something called unique factorization, which is crucial for a lot of algorithms used in computer programs. It's a bit like building with Legos.
Okay.
You have your basic building blocks, the irreducible polynomials.
Yeah. And you can use them to construct more complex structures.
Okay, that makes sense. So how does this unique factorization idea actually play out in the real world? You said it's used in algorithms.
Absolutely. Imagine you have a huge number you want to factor. It turns out that you can represent that number as a polynomial and then use these irreducible polynomials to break it down
Oh, wow.
into smaller, more manageable pieces. It's like having a special set of tools that help you work with really big numbers more efficiently. So it's not just a theoretical concept. It actually has practical applications in computer programming and things like that.
Exactly. A lot of the software we use every day relies on algorithms that factor polynomials behind the scenes, and understanding irreducible polynomials is crucial for making those algorithms work.
Wow, I had no idea. It's amazing how something as seemingly simple as counting necklaces can lead to these complex mathematical concepts that have real-world applications. I'm also curious about that formula you mentioned earlier for calculating the necklace sequence. It involved Euler's totient function,
Yeah.
right? Can you remind me what that is again?
Of course, Euler's totient function, often represented by the Greek letter phi, basically tells you how many numbers less than a given number are relatively prime to it.
Okay.
In other words, how many numbers share no common divisors with the given number other than 1.
Okay, so for example,
Let's say the given number is 10.
okay.
The numbers less than 10 that are relatively prime to it are 1, 3, 7, and 9.
Uh-huh.
So the totient of 10 is 4.
Right, I'm starting to remember this now, but how does this totient function tie into the formula for calculating the number of possible necklaces?
The formula is a bit complex,
Okay.
but essentially it combines powers of 2 with Euler's totient function to arrive at the necklace sequence. It's a fascinating example of how seemingly different mathematical concepts can be interwoven in unexpected ways.
It really is. And to make things even more intriguing, the OEIS entry mentions connections to other concepts like the Bruijn cycles, those things we touched on earlier, and unavoidable sets of binary words. I won't even attempt to explain those.
Yeah.
But it's clear that this simple necklace problem has some serious mathematical depth.
It's like a gateway to a whole universe of mathematical concepts and connections.
Speaking of gateways, I'm still curious about those field extensions you mentioned. They sound pretty abstract.
Yeah.
Can you break them down for me a bit?
Sure. Think about the different types of numbers we use: integers, rational numbers, fractions, irrational numbers like the square root of 2.
Yeah.
A field extension is essentially a way of creating a larger, more inclusive number system from an existing one.
Okay, so you're expanding the set of numbers you can work with. But why would you want to do that?
Sometimes you need a bigger playground to solve certain problems. For example, if you're working with equations that involve square roots, you might need to extend the field of rational numbers to include those irrational numbers.
So you create a bigger number system to accommodate those new elements.
Precisely. It's like building an extension onto your house to make room for more guests.
Okay.
And guess what plays a key role in understanding and constructing these field extensions?
I bet it's those irreducible polynomials again, right?
You got it. They act like blueprints, providing a systematic way to build these larger, more complex number systems.
So it's not just about counting necklaces or factoring numbers. These irreducible polynomials have implications for the way we think about the very nature of numbers themselves.
That's the beauty of mathematics. It's a journey of discovery that often leads to unexpected connections and insights.
Before we wrap up, can you give me an example of how these field extensions are actually used in the real world? It still feels a bit abstract to me.
Well, they play a crucial role in cryptography, which is the science of secure communication.
Okay.
Many encryption algorithms rely on the properties of finite fields, which are constructed using field extensions.
So those secure messages we send online, those are relying on these complex number systems built with irreducible polynomials.
In a way, yes, it's another example of how a seemingly abstract mathematical concept can have a profound impact on our daily lives.
Wow, that's incredible. I'm starting to see how this all ties together. We've gone from simple necklaces to digital circuits to abstract algebra and now cryptography. This deep dive has taken us on quite a journey.
It has, and it's a testament to the power of mathematics to connect seemingly disparate ideas and reveal the hidden order and beauty in the world around us.
It makes you wonder what other everyday objects might be hiding mathematical secrets waiting to be uncovered.
That's a great point. It reminds me of something we see in the OEIS entry about the minimum cardinality. It mentions that the minimum number of beads you need to create a necklace with all possible arrangements of black and white beads is related to powers of 2.
Interesting.
It's another fascinating detail that connects the necklace problem to the underlying structure of binary numbers.
It's like there's an endless supply of these fascinating connections, and the OEIS entry is just the tip of the iceberg. There are probably countless other mathematical rabbit holes we could explore, starting from this simple idea of a two-color necklace.
Exactly, and that's what makes mathematics so captivating. It's a never-ending journey of discovery where even the simplest things can lead to profound insights and connections.
Well, I feel like my brain has expanded significantly on this journey.
Yeah.
Before we wrap things up, let's recap the incredible path we've taken. We started with the question of how many unique two-color necklaces you can make,
Right.
with the rule that you can't flip them over.
Yeah, that seemingly simple question led us to the OEIS sequence, A000001, which opened up a whole world of connections.
We learned how the patterns of those necklaces relate to the output sequences of cycling shift, registers those fascinating digital circuits that keep bits moving in a loop.
Uh-huh.
Then we delved into the realm of abstract algebra, where we encountered irreducible polynomials, those prime-like building blocks that has implications for how we understand and work with numbers.
All right.
And we even touched on the concept of unique factorization, which is essential for many algorithms used in computer science and other fields.
Yeah, and just when we thought we were done, we discovered how irreducible polynomials help mathematicians build field extensions, which are crucial for things like cryptography and our understanding of the structure of numbers.
It's been an amazing journey, and I hope our listeners are leaving with a newfound appreciation for the beauty, complexity, and interconnectedness of mathematics.
I couldn't agree more. It's been a pleasure exploring these fascinating concepts with you and our listeners today.
If you're as intrigued by these ideas as we are, be sure to check out the links in the show notes. You'll find more information about the OEIS entry, irreducible polynomials, field extensions, and all the other amazing things we've talked about today.
And remember, mathematics is all around us, even in the most everyday objects. So keep exploring, keep asking questions, and keep diving deep.
Until next time, happy exploring.